We can start.
Yeah, welcome everyone for this live session of the course series VLSI design. I'll be happy to answer your questions in this session. If you have any doubts about the course content or any other aspect related to the course, please put your questions in the chat box. We'll take questions one by one. I So in this second part of the course is very interesting. I hope you already enjoying this part of the course. But initially I taught about this various optimizations that are available in high-level synthesis, and then it's not only the availability, it's how to utilize them, right? So that is very important. So just randomly applying optimization may not give you the desired performance, right? So what I did is I take two case studies, two classes where I just take certain case studies and has shown that how we can actually apply certain optimizations and how it's getting impacted the synthesis results, right? And also I have taken this matrix multiplication application where we basically shown that how to make sure that this we can generate a efficient hardware by a kind of doing a applying various kind of loop optimizations like loop tiling and then unrolling, and also just making sure that this whole matrix multiplication break into small component and then they are running in parallel. So these are the things that I have taught in the class, and I hope you enjoy that part of the course. It was informative. And also I have taken certain recent advancement in the high level synthesis as well, where I talk about the verification of high level synthesis, and you know that this the current practice of verification of high level synthesis results is nothing but simulation test, right? So you basically you verify your SIP specification with some set of test cases, you synthesize the same to RTL, and the high level synthesis tool automatically add wrapper to the test bench so that this can be used for RTL simulation. And then you can use the inbuilt simulator, RTL simulator of the high level synthesis tool, or you can have any commercial tool like models, and you can simulate and just check whether your RTL is also have the exact output. But as I mentioned in one of the course class that it was basically very slow, right? The RTL simulation is slow. So one new work that my group has done on that, basically you reverse engineering a C code from the RTL. And remember that this C is not the original C that we're getting back. What we're doing, we're representing the hardware in terms of C code, right? And basically here the advantage is that this C code as the variables are nothing but the registers uh, of the RTL. Similarly, the array is nothing but the RAM ROM of the RTL, and it is also cycle accurate, because what we are doing is here is that we basically take the FSM controller FSM of the this RTL, and then every state we try to extract to identify what is the operation is happening in the RTL, and then we identify those register transfer level operations, and then this FSM become FSMD, right? Final state FSMD. And that FSMD is nothing but a CDFG, basically control data product. So we use that, we actually rewrite that CDFG in terms of C, and then use the GCC compiler just to synthesize, just to simulate the RTL. And we have shown in that work that this is basically have all the features that a RTL simulator has, and it can actually it can actually also do a cycle accurate simulation of the RTL. It can also debug friendly because all the variables are actually the variables registers of the hardware. So that is very interesting work, and that can actually have a very much potential to speed up the whole high-level synthesis verification process. We have also discussed about the verification of high-level, formal verification of high-level synthesis. So I was basically still in the research mode. There is no commercial tool available, so it's a good area to do a research as well. So in one of the lecture we talked about the verification of all the phases of high-level synthesis, and then in another class we talked about the end-to-end formal verification of the high-level synthesis. And then we also Next week we take the security aspect. So you know that nowadays there are a lot of problems with the security, right? So basically, the third is IP piracy. I hope you all know aware of this fact of IP piracy and overbilling. The concept is very simple, and there is no options unless you do some kind of secure design. Right? So the idea is that you develop your IP whether through high level synthesis or you write your RTL directly. You do all this logic synthesis, physical synthesis, and you have that layout. You have to give it to third party, right? So because not every electronic company has their own fab lab, right? Which is very costly. So what usually happen that that particular fabrication lab, there may be some untrusted employee who can actually steal your IP. It can pilot your IP, can overproduce the IP, and it can harm your business, right? So the idea that we have talked about is the logic locking is very novel approach and very important concept. Is basically nothing but you add some extra key and you lock your design basically. Right? So you add some extra gates in your design so that your circuit is now locked with a key, and only this circuit will work for one correct value of the key. Right? So if you give that correct key, it will give you the correct output. Otherwise, it will just give you garbage output. Right? So, and once you give that the layout to the third party fabrication lab, you don't give the key. Right? So even if he can reverse engineer and get the netlist, he won't be able to use it. Right? So that's the advantage of this logic. And we have told that we have actually in this class we have talked about how we can use high level synthesis to automatically generate a locked RTL, right? So it's automatically decide how many the key has to add and where to add and how to modify the RTL and generate that RTL. So that the biggest advantage of the whole process is that now your circuit or the design is locked from the early in the design flow and to remain locked throughout the design flow, right? So it is really makes sure that this IP piracy and overbuilding is difficult with this logic, right? So that we have talked about that we have talked in this class, and then finally I just talked about some recent advances of high-level synthesis, which is the last week, and also have some brief overview of the Fpga synthesis, what is logic synthesis, what is physical synthesis, and then what are the kind of RTL optimizations are available in the synthesis tool. So those are the things I just talked about in briefly. So that was the second part of the course, and I hope you are learning and enjoying the course. So let me take the questions. So Ramya Ramakrishnan, target time is that, so you have to have achieved, so when you develop a design, you have to understand that this IP is not, or that RTL you are going to design, it's not an independent component, right? What is that? It basically has to be integrated in a SoC, system on chip. There will be many such IPs which will be integrated, right? And then there are some time requirement that the input of that particular IP that you have developed, probably having some input is coming in certain frequencies, or the block that is actually taking input from this particular IP probably has a certain expectation, right? So they are expecting the expecting the output in certain level, inputs in certain frequencies, right? So in that sense that so once you try to develop a RTL, you always have some target frequency in mind that I want to achieve say 100 megahertz, right? And then you synthesize your hardware, right, through high level synthesis. And then this high level synthesis do some estimation. It may not be exactly accurate because until you do the logic synthesis, you may not be able to do the physical synthesis, you are not able to get the exact clock, but these tools are smart enough do some kind of statistical analysis and then they can give you certain kind of estimated clock. But how this clock actually determine the clock that this if you take this RTL, you can achieve this much of clock, right? So suppose your target clock is 100 megahertz and your circuit is reaching only 70 megahertz. So how it determines? It determines based on the critical path or the max critical path in the circuit, and I hope you are aware of that. It's the maximum path, combinational path between two sequential elements, right? So it basically identify the RTL and identify what is the longest path or the path which is the maximum delay, and from the delay it just say it is 1 by delay is the frequency, right? So it just estimate this is the target clock I can achieve, right? So and then if you say you if most of the time if your circuit meet the target clock, that means you are done, right? If not, you need to know what are the kind of optimization that you should utilize or use to uh, use the improve the timing of the behavior, right? So that things you have to understand, and then you can actually improve the estimated time. Okay. So Suraj Konsam has a question. So Suraj is asking, sir, where we can find demonstration of programs for implementing hardware accelerator using Vivado HS. Okay. So yeah, so obviously it's kind of there are many research paper which you need to start reading, and then you can actually understand how things are being achieved. But there is a good book. Let me just you can search it here, right? So let me just search and I'll give you the link here itself. I'll give. So there is a book. I can use that one, right? Just a second. I'll give you a e-copy e-book, which is really great book on this. The topic, exactly the question that you asked. Yeah. So can you please copy this link in the chat box? Yeah. Okay, search. There is no control here. Yes, search FPGA parallel programming. FPGA, GA, parallel programming. Yeah, the first. So please copy this website link into the chat. Okay, so I have pasted the book that I was referring in the last live session as well. So this is a great book. I will suggest this is something if you are really interested to understand high-level synthesis or how to utilize the optimization of high-level synthesis. This is a very great book. It's open source. The PDF is available, so you can read this. So what this book has done is taken certain example like this matrix multiplication, FIR filter, many other applications, and then it just shows that how iteratively you can actually improve the. You just generate the RTL, then you apply this optimization, then you get these optimizations, and they actually give the intuition why you should apply this optimization to improve the performance, right? So if you are really interested, Suraj, you can actually refer this book. There are many examples, and you will become smart high-level synthesis user if you just follow this book. So Remaya has another question. What are the factors to be considered to choose the target device should be selected for an implementation? Okay, another good question from Remaya. So see, this what is the target device, right? So this target devices is basically the FPGA board, and there are FPGA board which cost 10,000 rupees, and there are FPGA board which called 10 lakh rupees, even more, right? So why the cost differs based on the resource, right? So if you buy a 10,000 rupees FPGA board, it has probably has a very limited number of LUTs, limited number of DSPs, limited number of RAM and ROM, right? But if you buy a 10 lakh rupees board, it has more number of resource, right? In terms of this DSP, RAM, and LUT. It's not only that, there are certain board which can actually have also some processor, right? So you can actually execute some part of the C code in a processor, the FPGA board itself. So it depends on your target. So if you are taking small examples, you just choose any. I mean, specifically, when you are actually learning high level synthesis, the device doesn't matter to us, right? So usually we take very small example and you can fit it any available board, right? But if you are actually taking a very practical design, say, and then you need to understand what device target I should select it, because it depends on the resource you need, right? So if you need a very big application, so you need hundreds of multiplier, and if the target device does not have those many multipliers, so you have to choose some other board, right? So this is basically for commercial purpose who develop big IPs using high level synthesis. They are for that the target device is important, but usually for academic purpose we usually don't care. We can just select something. Okay, so I hope it answered your questions. So one important aspect I just try to tell you that you must download this Vivado HLS tool from Xilinx website, and it has a Webpack edition which is free basically. And as it's in line with the Remaya's questions, in this free version there are many target devices not available, only a very limited number of board is available, and those boards are basically have very limited resource. So if you try to take a very big example, you don't able to synthesize it good, but for academic parts, as I mentioned, it's good enough. But please download Vivado HLS tool, install in your machine. Its size is big, I think 6 GB to 8 GB around that, but it doesn't matter. But you should have been, unless you actually run certain example in high level synthesis tool, you won't learn how the optimizations, or you know, I mean rather you won't be able to appreciate whatever I am teaching, especially the optimization part, right? So you take an example, you synthesize it, you create some test case, and you do the C simulation, you do the RTL simulation, then you will understand if there is any bug is happening, and you can also see how the RTL simulation is happening, and then you try to apply the optimization, data flow, loop pipelining, loop unrolling, array partitioning, so many other things, right? So you try to understand that. Sometimes you try to modify the input C code. You see that you apply loop pipelining, you try to achieve initiation interval of 1, but you're achieving say around 10, 8 something. So then you have to understand what is the dependency. Most of the time it's because of certain dependencies, array access causing that loop pipelining causes problem for the application, the loop pipelining, right? So then you have to understand what is the problem, and then probably sometimes you have to apply do some manual modification of the code or rewriting the code, so that this become that particular problem get resolved, right? So I request all of you, you must download and try, right? So that is really useful, and usually in my this course I taught here and there, I usually have project. What I usually do, you just search for actually high level synthesis benchmarks. There are many benchmarks. You will get CS Stone benchmark, MI benchmark, even there are many others, right? So you can just take the benchmark from there, and there are certain paper which actually talked about how this benchmark performs on Vivado HLS and all. So you can download certain papers, and then you can just do the similar kind of job on your own, right? So that will really help you to understand the internal of this high level synthesis tool. So that is kind of must, but in this virtual mode, it's basically your own initiative, right? So I request all of you to do that. So there are a couple of questions now. Bina has certain question. What are the research based topics nowadays in HLS? We have licensed Vivado HLS in our institute and PG board. Yeah, that's great. So high level synthesis, as I mentioned in my introductory video as well, it's become very popular in recent times, right? So the primarily because of the generation of hardware accelerator, right? And if you look into the top tier conference journal in the VLSI domain, you just search the DAC, date, identity transaction on CAD, ACM today's transaction on VLSI. You will see so many papers coming which are actually using high level synthesis to develop efficient architecture, say for CNN application, DNN applications, image processing applications, domain specific language, right? It's not only C2RTL, right? So I'm seeing certain paper where people are actually trying to use say Python code, right? So you write certain machine learning algorithm in Python and then you try to synthesize them, right? So and uh, and there are many domain specific language. I mean, specifically for image processing domain, there are language which basically helps you to write your application very easily, right? So in those kind of domain specific application, also how to efficiently synthesize those domain specific language into RTL. That is also another domain. The domain there where I work, verification of high level synthesis. There is no still or tool who can check C2 RTL automatically till date. Right. So you can always try that to check that serious security aspect in high level synthesis. There are so much of work on side channel attack and all, right? So can you generate RTL which you can say there is cannot be during time in channel, there is no power channel. Can you generate certain such RTL from high level synthesis, right? So you can modify your scheduling algorithm, modify your register algorithm such that you do not have any power channel or side channel, right? So there are so many areas you can work on, right? And I can tell you honestly that this is a very exciting area to work on now because new application is coming, security aspect, verification aspect, domain specific hardware accelerator. So many things are there. So if you have, and the basic thing is that the fundamental is very simple, right? You have to understand the basic logic of this data flow, loop pipelining, array. These are the three pillar, right? So if you understand that how this get efficiently get synthesized, you are done, right? Thus you can actually apply the same medicine in all domain, right? That is the kind of thing. So if you understand the core concept of high level synthesis, you can actually work on this domain. So I mean, to be honest, this is a very exciting area. You can actually choose this as your research domain, and you can start working, right? So there are a lot of areas I mentioned. Abuzar Khan has two questions. There are three questions. So, look like software developer, data structure, and algorithms are important. Uh, so it depends on what is your expertise, right? So if you try to see, there is a question that I usually ask when I was in industry. I used to talk with my seniors in the industry that who is going to use the high level synthesis tool, right? So see, if you are an expert RTL developer, do you want to go to write your specification in C and use high level synthesis? It's very difficult to convince those people, right? Then there are certain of people who write applications in high level and then try to synthesize because this the general processors are slow, right? So sometimes they may not achieve the targets. Specifically, think about the machine learning applications. Right? We are always talking about so much of architecture which actually fits in for machine learning applications, right? So then you think of I want to generate quickly RTL and you don't have much knowledge in RTL. So those are the people mostly going to use the high level synthesis tool. And then basically you being a software developer probably you have that knowledge, right? So you have that knowledge how to write the specification in C. But you don't know what you don't know is that if I write this way, whether it will be and if I use the high level synthesis tool to generate hardware, whether it is an efficient hardware. So that is the part you have to learn. So if you are an algorithmic developer or application developer, and if you want to use the high level synthesis tool, the things that you have to understand, I mean, you have to spend a couple of months to understand, figure it out that this is the problem. In my C code, if this is the nested loop is the problem, arrays this is the problem. Pipelining, these are the dependencies cause the pipelining stop, right? So these are the things if you understand, then you can utilize the high level synthesis, right? So, so obviously, but if you try to use the high level synthesis tool, you do not need to become an expert of that in that data structure and algorithm, right? Because somebody is giving you the specification, right? And learning, you don't need to know the data structure to be honest, very that way. Only thing is that if you are an RTL engineer, you try to use high level synthesis tool, your specifications should be in high level. Most of the time, these specifications are available in any textbook, right? You can just take it from textbook or online resource, and then you try to use it high level synthesis. So, to answer the questions of observe precisely, I don't think you need to be an expert in software data structure and algorithms, but basic knowledge is always useful. Should I, as HLS designer and engineer, basics of digital design are important? So do I still need to have the knowledge of data structure? Yeah, so basically it's a interface from the software and hardware, and to be honest, you need to know both. And good point is that you don't need to be an expert of both, right? So because this is a domain where things actually converted from software to hardware, right? So this is where adaptations happen. So in my C, for example, I work in high level synthesis more than 10 years now. I'm not an RTL expert, right? I know the digital design. You give me a circuit, I can understand what is going to happen there. But if I ask me to develop a big RTL circuit, probably I'll take a lot of time to do that. So I'm not an expert in RTL design, but still I'm using high level synthesis quite efficiently for a long time, right? So basically, it's basically on to answer your question. To become a hard HLS design engineer, you need to know both of them a bit high. I mean, in high level, right? So a basic knowledge of both is needed, and specifically the relation, right? So if this is my loop and if you get mapped to hardware, so this will cause a problem. Here I should apply loop pipeline, here I should do unroll. If there is a three nested loop, I should tile certain things and then I do unroll. So this is the kind of concept, and if I do that, then my hardware will be efficient, right? So this kind of correlation between the software to hardware is very important, and you have to just always think, okay, if I do that and try to do it in hardware, what is the problem? Can I achieve the similar what is happening in software in hardware? It's not, right? Because software is sequential and your hardware is parallel. So you have to always try to understand that how can I write my C code so that it will be easy to parallelize those operations. Right? So these are the things you need to understand. I mean, as I said, you need to invest some of your time. It's not that without understanding the code of high level synthesis, you can use it efficiently. Obviously, no. But I would say this is much easier because you don't need to know in much depth of RTL design or software development. Right? So having a balance between this basic knowledge of algorithm data structure and digital design is sufficient. And specifically, if your background is computer science, you have perfect match. Right? You have both the things. You have data structure in your course. You have also digital design in your course. Right? So that is more than enough. Absar has one more questions, or any particular high level synthesis algorithm to work on high level synthesis. See, so there is another angle. So basically, if you try to develop a high level synthesis tool, you need to be expert of high level software development. You need to know all the data structure algorithm part and parcel. Right? So that is another aspect. So you want to develop a high level synthesis tool. So it's basically depends on whether you want to use the high level synthesis tool or you want to develop another high level synthesis tool like Vivado HLS, right? It depends on your objective. So if you're a software developer, you want to develop high level synthesis tool, and so you need to know compiler must, because the interface is a compiler, right? You need a compiler that will convert that C code into some IR, intermediate representation, from where this whole process of high level synthesis starts, right? So you need to understand that, and then efficiently the scheduling is an NP complete problem. This register allocation is an NP complete problem. So how to, you need to know what are the good heuristic based algorithm for scheduling allocation and how to efficiently implement them also, right? So what is the efficient data structure to implement those things? So developing a high level synthesis tool, you need to be an expert of data structure and algorithm. But if you want to use it, as I mentioned, you need basic knowledge is good enough. Suraj has another question. There is a HLS for ML project of converting Python to RTL using Vivado for FPGA target. How is this different from using directly coding in Vivado? So this Vivado came with a BTs recently, right? So where they actually provide certain IP for machine learning, right? So basic idea is that they already develop certain efficient implementation of certain very common application in machine learning, and then when you synthesize them, they are going to utilize those IPs, right, internally. So, but yeah, it's a good point that Suraj has read. So you should also, because if your target is a machine learning application, you should use BTs because it already has some inbuilt IPs, right? So you can utilize for your generating efficient hardware, right? So that is something also you should use. Akash has a question. I am an RTL specialist, so do you suggest me to directly go to with RTL if I am doing my final year BE project in hardware accelerator domain? Yeah, it's a tricky question. So, uh, I'll to answer my your question is that, see, you to do a, say you try to implement a specific application in RTL, you need a lot of time to understand what is the architecture I'm going to take, and then how I'm going to plan my architecture. So just like your you have to plan your whole design, and then you have to understand how many, what is the latency will be my design, or how many resources I'm going to use. You have to do everything on your own, right? And then clock, all these detailed things you need to know, and it needs a lot of effort, right? And then think about the same application. If you have it's already there in the application is already written in C or Python, you can actually, I will suggest it will take less time to get an RTL because Vivado will give you in minutes, right? But then if you spend, say, 1 week or 2 week on understanding this optimizations, and then you just modify your C code, right? It's not modifying your RTL, it's modifying your C code, and you can generate different RTL. And specifically, this high-level synthesis has the advantage of design space exploration, right? So what is that? Just changing two optimization, you can get completely get a different architecture, which is not possible when you try to do it until. So as an, I think it's a BE project. You should actually explore, and probably by just doing a BTech project, you become a master of hydrogen synthesis, right? So probably you get an RTL, which is you feel that it's not good enough, and then you try to tune your optimizations, and you're getting different architecture in minutes, right? And then you can compare their performance because you're an RTL engineer. You can probably look into their schematic, try to see what is the critical path, where it's going wrong, and probably you can actually make out, oh, this is the problem, this is the where this hydrolysis this is not doing well. So let me apply that optimization, right? So since you're an RTL engineer, I mean electronics background, so you can always, this is a schematic, analyze the critical path, and come back to high-level synthesis and apply the optimization, right? So that is the advantage that this specifically this EC background, triple background, who have the good knowledge about the very law RTL, they will get it, which the computer science students struggle, right? So they won't understand why I'm not able to achieve my target clock, right? So probably they will not able to analyze the critical path and how to eliminate such critical path things. So where probably you have a better, you are better equipped. So I will strongly recommend you to take this as a challenge that in my BTech project I'm going to use HLS tool to develop IPs, and probably will learn more when you actually take a particular application. As I mentioned that just analyzing the RTL and see where probably could have been, you can see how many errors are there, how many are getting used every clock, right? You can understand, make out, oh, this is the problem. This error is even ideal for most of the time. Let me do something, right, in my C behavior so that my resources will be utilized more, right? So these are the kind of things you can do, and you will not invest your time on developing RTL because that is automated here. Only thing is that you have to understand why my RTL is not good enough, right? What is the lack? What is the problem? So that will give you a lot of expertise as well. I'll suggest because you will become an expert through this process. Okay, so Riyaj has one more question. That, sir, I have completed C language now. For which language I should go with? See, C and C++ is same, so almost similar, right? And to be honest, these high-level synthesis tools primarily do with all these tools that they are in the commercial market. They they do well for specification in C, C++. There are certain open source code which can take TensorFlow things, or there are certain software like Symfony model compiler that takes Simulink as an input rather than C. But I have, as per my understanding, the best input to high-level synthesis is C, C++, right? And there are certain other tools like, say, Model C, even I think Vivado HLS, they can take System C as well. So you can actually try those System C inputs, what is the difference, what are the other aspect which is not there in C++ playbook, right? So these are the things you can try, but trying from Python or say Simulink, I don't think that's not so popular. So rather you can actually see what are the other common language which from where actually high level this is generate efficient hardware. So that you can try. Remy, I have one more question. So for an implementation using Vivado HLS, Vivado VTS HLS, shows the resource usage. Yes, LUTs and FF only, but the estimated time is showing as 0 nanosecond. I could not find any error in the program. Okay, so I mean, to be honest, I have not used VTC yet. So we have extensively using Vivado HLS for our all research project. Uh, you can actually see the design manual, what about what they are talking about the estimated time. Usually it shows some estimated time. So I mean, latency sometimes they cannot show it. You know that if there is a for loop or while loop basically, where your the loop bound is not is an input, right? So tool do not know how many times the loop will iterate. So then it cannot give you the latency. So high level synthesis tool does do not only give you the this the estimated time or the clock, target clock, what is can be achieved. It also gives the latency, the number of clock you need to get the output, right? So the latency sometimes is not available for specific input where there are loop which is not bounded, or there are if else where the operations are which is not kind of balanced, right? But in general it gives the time. So probably I mean, what I suggest you can actually see the design manual, the user manual of this VT the new tool which I have not used yet, and you can see whether they actually why they are not giving estimated time or is there any reference there on that. Right? But usually this can give it, or maybe it is a free version why that is why it's not giving. I don't know because if there are say there are IP that is using, so probably they don't want to reveal that, right? So it may be that there are some IP they are using which they don't want to reveal the latency and all. So that may be the reason. I am not very sure to be honest. You should go into the design manual or user manual and check what is the exact reason. So media Atiak. Okay. I hope it is your nickname. Sir, what is the recent and future trends of VLSI? It's a very open question, right? So, um, see, in the high-level synthesis domain, I have already talked about certain aspect, and I think that's the trend everywhere. So, the first thing is this hardware security. So, in the hardware security, there are two aspects. One aspect is this hardware security against this IP piracy overbuilding, and another is basically developing uh, hardware for hardware the security, right? So we implement efficiently that security like cryptographic algorithms like AESDs and all, right? So those are there are so many things. The lightweight because if you try to give a DES or AES encryption in a tiny IoT chip, you have to give a lightweight version of that, right? So how to implement a lightweight version of those cryptographic algorithm, which can give you, which can fit into IoT devices or tiny devices, right? And similarly, there are concept of approximate design, where basically you say ki my output is 10%, there are 10% error, but it's okay because in certain application 10% error is acceptable. So this approximate design specifically for the tiny device like IoT application is another area where people are working a lot. So that's the security angle. There is another big area which is opening up is the this quantum computing, right? So you know there are quantum computers are there. So now quantum circuits, quantum circuit automations, verification, testing, these are all a very new area and it's very exciting area to work on. So you can actually check this quantum computing and quantum circuit synthesis areas also. So security is a big concern. There is another security angle is the hardware trojan, and I hope you already heard so much of news on these hardware trojans. Specifically, there are when you buy certain IP or the device from a third party which is not trusted from a particular country, I don't want to take the name here. So, and then they might have some unwanted hardware is inbuilt in the chip, right? And then it can do something. It can say can do some unwanted scenario, right? If you think about this power, I think there are so much of this power grid. There are so much of news of this power grid, right? It goes off. It's not performing, and most likely there will be some hardware trojan there, right? So suppose you want to switch off certain power unit, but because of this hardware trojan, it's not right, or suddenly it's just switch on, which is not needed. So much of this hardware trojan can do harm, and then this hardware trojan detection in the runtime hardware trojan detection or design time hardware trojan detection. So those are the areas is very still very live. And I think the another most important area where people are working is the hardware accelerator. Basically, I mean, this is again I talked about in my introductory lecture that initial trend was this general make the general purpose processor powerful, right? But that was not scale up because of the this technology scaling is not feasible at a certain point of right. So Moore's law fails now, right? So and then you take a lot of power, it get heated up, it can burn, your IC get burned, right? So then it's come back to the concept of this parallel processor, right? So you put more cores, right? So octa core, dual core, octa core, so many cores are coming. So instead of making one processor very powerful, you make many processors small and then you connect them and they work in parallel. Right? So that's the things was happening in 2000s, right? 2004 to 2015, I would say. And then but that has a limitation, right? Because when there are you can add 16 to 32, 32 to 64, but lot of synchronization problem, communication, this data coherency. There are so many other synchronization issues who come in with that, right? So and it's not that if you increase your code from 32 to 64, your performance will double. It's not, right? So there is a limit again there because of the synchronization problem. So then these people are actually trying to do this hardware accelerator, right? So it's basically you develop a very cheap, small processor which can do a particular job very efficient. It does not do anything else, but it does do a particular job very efficiently. Say this image enhancer, noise cancellation, this many AI applications, right? So that was something is a very active area of, nowadays in VLSI also. So how can you generate efficient hardware accelerator quickly? The term quickly is very important here because there are a lot of competition. Right? You have to come up with a efficient hardware accelerator as soon as possible. Right? So that's the ball game, and there are a lot of work is happening in that area also. So kindly, so I probably know my name, right? So my name is Chandan Karfa. If you just search in Google, you'll get my website and you can get my email ID, right? And please contact me if needed, right? So if you need any technical help, academic help, I'm always there to help you. So please be in touch with me in my official email ID, which is ckarfa@iitjc.in, and you can Google it and get it that. Okay. So I hope that answered your questions. Uh, okay, there is one more question here, Suraj. I implemented ReLU in Vivado HLS with a test bench. The latency is 0. I imported the IP to Vivado HLX and want to do behavioral simulation. How will I get the input and clock to the generated clock? How will I give input and clock to the generated clock? I will suggest you actually do this logic synthesis, right? So once you do that, you can actually get the latency as well as the this clock, right? I think that is something where, and I mean, one thing I'm just uh, maybe you just check the warning message that is coming in high level synthesis, right? So if there may be something you're missing somewhere. Because of that, probably it's generating some RTL, but it might have some bug, right? So whenever things get synthesized, probably you can just check the log message, what is coming there, and then you can understand that probably you're missing something somewhere, right? So that's something. I mean, I understand the latency, because latency sometimes they cannot estimate, but clock usually they give. So there may be something you are missing somewhere, but other than that, you can actually do the RTL simulation and understand what is the latency, and then you can actually do the logic synthesis and physical synthesis, and then you can actually get the kind of target block which you can get it, right. So from that information you can actually move to this HLX. Okay, I hope it answers your question, Suraj. Uh, I have the question of media ADX or something. So suggest something, sir, because I've already given so many options, right, from your first question. Uh, Contact details I've already mentioned here. Ashish has a question. Please guide how to implement an efficient network on chip design parameters. Uh, Please guide how to implement an efficient NOC design parameters like latency, area, and more. So there are certain simulator, right? System simulator. I know that GemSim. I think you know that. So you, I hope you are talking about that only. So usually people do develop this NOC in those kind of simulator, where you can actually choose the number of core, uh, the kind of routing algorithm you want to apply in the NOC, and the kind of the number of channel, number of virtual channel, and those things you can actually decide on those particular things. And also even in the processor level, what kind of cache you want to use, how many level of cache, because this in the NOC the number of page fault, where you actually try to transfer the data from other processor, depends on the number of page fault, right. So those things you can control. So I think to answer your questions, probably if I understand your question correctly, is you need to take certain system simulator like GenSim, which you have to understand, and it is free basically, and you can actually simulate your NOC design, and there you can get the latency, power, all the information, and probably you can minimize them based on the simulator output. Is it answer your question, Ashish? Okay, I think a lot of interest. I'm really happy that people are getting interest in high-level synthesis, and I sincerely believe that this is something is going to be a big uh, important area for uh, in the recent area, recent research area in the VLSI domain in the recent time. So it will create a lot of other applications through high-level synthesis. So I hope the learning that you are having through this course will be useful for your future career as well if you are a student. Okay, so I think there is no more questions. So if you have any question, please put your questions here. Otherwise, we'll wind up into another 2 minutes. There is one more question. I am pursuing my masters in VLSI. I am interested to working in the backend as analog. Is there possibility to link HLS in backend? I don't think so, because in analog, because high level synthesis generate RTL, I don't see there is much scope in high level synthesis for these analog engineers. Okay, so thank you everyone. Please continue the learning in the course. So, if you still doubt, please post in our discussion forum. We usually answer within 24 hours, but please understand that we also have other other commitment, and sometimes the tea are also busy in the exams. So sometimes we miss that deadline of 24th, but please post your question. All questions will be answered, and also most of the time I also look into the questions and answer whatever is needed. So please feel free to uh, reach us through our discussion forum in the course, and also if you have any further guidance needed, you can always reach me in my personal website also. I will happy to help you. Thank you.